Okay, so we're going to take a look here at this particular problem where much of it has already been done, but we're going to pretend that it hasn't been done. So there we go. So we're supposed to balance this reaction, and I'm going to cross out these coefficients here so we can see how we come about to realize that those are the coefficients. So here we have one sulfur. That's good. 4 fluorines, 1 fluorine. So we're going to put a 4 here so that we have 4 fluorines. Here we have 2 hydrogens and 4 hydrogens. So we're going to put a 2 here so that we have 4 hydrogens. Here we have 2 oxygens and here 2 oxygens, so this is balanced. Now we're supposed to name each of these. So to name each of these, we give them the binary molecular name. So this one is sulfur tetrafluoride. The first element in the formula gets the name of the element, and you use a prefix if there's more than one. The second element gets the "ide" name, and you always use a prefix. So sulfur tetrafluoride. Here, this one, there's 2 hydrogens, so we get dihydrogen. And then this is oxygen, so 1 monoxide or monoxide. Here, sulfur dioxide. No prefix because there's only 1 sulfur. And here, hydrogen monofluoride. Now, some of these have some common names. For instance, the common name of this guy is water. And the common name of this guy is hydrofluoric acid. All right, so this next one, if you look at the evolution here, we have 1 nitrogen, so that's good. 3 hydrogens and 2 hydrogens. So what we ended up doing was we put a 3 here and a 2 here, so that we would have 6 hydrogens and 6 hydrogens. And then we have 2 oxygens here. And since we had a, oh, I'm sorry, I have to go back. Change that to a 3, change that to a 2. Here, since we changed the number of hydrogens, we had to come back here and change that. Is that right? No, since we put a 2 here, now I'm all confused. I'm just going to cross all of these out and start over. How's that sound? All right, so I'll write the numbers below. 1 nitrogen, 3 hydrogens and 2 hydrogens. So I'm going to put a 3 here so that I have 6, and a 2 here so that I have 6. But now I changed the number of nitrogens, so I have to go back here and put a 2, so I now have 2 nitrogens there. Here I have 2 oxygens and 3 oxygens for 5, and I only have 2 over here. So how do I get 5 oxygens over here? I put 5 halves there. Now we don't want a balanced reaction with a fractional coefficient. So what we do to keep everything the same is we double everything. So I'm going to call this 4. I'm going to call this 5. I'm going to call this 4. And I'm going to call this 6. And we can double check the coefficients to make sure that we have a balanced reaction. So 4 nitrogens here, 4 nitrogens here, 4 times 3 for 12 hydrogens, 6 times 2 for 12 hydrogens, 5 times 2 for 10 oxygens, 4 times 1 for 4 oxygens, but 6 times 1 for 6 oxygens for a total of 10 oxygens. And then here are the names. You'll notice above, this guy was called hydrogen, dihydrogen, and this one's called dihydride. And the reason for the 2 different names is because in this case, the hydrogen is the first element, so the name is the name of the element. Here, the hydrogen is the second element, so it becomes the "ide." Oxygen alone is just oxygen. Here we have nitrogen monoxide, and here dihydrogen monoxide. And here's the results of the second one or third one. I didn't bother naming this one or this one. Here, you wouldn't know the name of that. You'd have to look it up. It's boric acid. Okay, the next question is about equilibrium. Let's see. Identify each of the following statements as either true or false. You can see that the word equilibrium is in each of these statements. So let's take a look at equilibrium very quickly. So this is an equilibrium reaction right here. And a lot of times for equilibrium reactions, you put these little arrows here, forward and backwards. Now, technically, all reactions are equilibrium reactions. It's just that some of them pretty much react all the way or never react, okay? So those aren't really called equilibrium reactions. The real equilibrium reactions are when you have a measurable amount of each of these. Okay, so here the top arrow is called the forward reaction, and the arrow that's going backwards is called the reverse reaction. Now, when you have an equilibrium, the rates are equal. That means the forward rate equals the reverse rate. So if one of these reacted every second and made these two things, two of these would react every second and make one of those. So imagine if you had 10,000 of these and one of them came apart every second. And imagine you had 10 of these and 10 of these, and one of each of those came together every second. That would be an equal rate. And you'll notice that the numbers I put up here are not equal. Okay, we don't have to have equal amounts of reactant compared to product. Just the rate has to be the same. So I want you to imagine if we take a look at a graph of the rate of reaction over time, and we assume for this graph that we have only reactant at the beginning. So no product. So what's the reverse rate going to look like at first when there is no product? And the answer is the reverse rate is going to be 0 because there are no product that can react. So the reverse rate is 0. The forward rate will start at a pretty good clip. But as soon as one of those forward reactions occurs, you've got less of the forward, so the rate decreases. The less you have of the stuff, the slower the rate. So the forward rate is going to decrease as we start making more and more product. But as we start making more and more product, the reverse rate is going to increase because you get more stuff to react. Now, as the reverse rate increases and the forward rate decreases, eventually the rates will be the same. And what will happen is that the amount of product and the amount of reactant will stay the same. And that's why it's called equilibrium. So here, when we look at this time graph, over time, there will be a point in time when the rates are equal. And that's called equilibrium. Okay. Now, likewise, we can take a look at concentration versus time. So concentration means just how much of the reactant and how much of the product you have at a given time. So this time, of course, is 0, and this is over a long period of time. We're assuming, again, that we start with only reactant and no product. Now, for the reaction I wrote, it looked like this. And I invented some numbers of 10,000, 10, and 10 when the rates are equal. So here, for the product, we've got nothing. For the reactant, we have a whole lot of stuff. Now, as the reactant reacts, what happens to its concentration? It decreases. What happens to the product? Its concentration increases. So this could be one way that this graph could look. But there are other ways this could look. The important thing about this graph is that once we reach a certain amount of time, the concentration is constant. It does not change. And this is the equilibrium part of the graph. And this is approaching equilibrium. Now, this is one way to draw the graph. It could happen a lot of different ways. So I'm going to draw 3 different graphs over here. This one I will redraw again. So here we're starting off with all reactant and no product. So this is product, this is reactant. It could go like this. So again, what do these 2 graphs have in common? And that is beyond a certain point, they remain constant. And it could be something like this. So here we have 3 different graphs. Now at equilibrium, when you have more product, this is called product favored. Here, when you have more reactant than product, this is called reactant favored. And here, this is neither product favored nor reactant favored. You have about equal amounts of each. Okay, so you can have any one of these 3 types of equilibrium reactions where it's product favored, reactant favored, or really neither favored. Okay. So let's take a look at this statement now in light of what we've just looked at and see what we can figure out. All chemical reactions are product favored at equilibrium. Well, we just found out that no, some are reactant favored. False. There is no observable change in a chemical system at equilibrium. This could be answered 2 ways. If we want to talk about concentrations, then it's true. If we're talking about reaction occurring, then it's false. So I believe that they intended this to be there's no observable change in concentration in a chemical system at equilibrium, which would be true. The concentrations stay the same. All right. Now, if they had meant there is no reaction occurring at chemical equilibrium, that is patently false. At chemical equilibrium, both reactions are occurring, but at the same rate. Okay, in equilibrium involving a weak acid and water is product favored. Well, what is a weak acid? And that makes me want to think, what is a strong acid? This is a strong acid. When it reacts with water, it forms something called the hydronium ion. Now, if I put 100 of these into water, how many will react with the water and do this? All of them. So there are 2 words we could use for that. They 100% or completely ionize, because here there are no ions before and now there are ions. We could also use the term dissociate, because sometimes this is written this way. where this hydrogen is analogous to this H3O plus, the hydronium ion. This is just a simpler way to write it. Is this happening in water? No. But again, it's simpler. Okay, so that's what a strong acid does. Notice I put for the arrow one way. Even though technically this is an equilibrium reaction, this is so product favored that we say there's essentially no reactant left over, no HCl left over. Now, an example of a weak acid is this. It's called acetic acid. You find it in vinegar. When it reacts in water, this is what happens. So this is incomplete or partial ionization or dissociation. Another way to write this is this way. Okay. Now, when we talk about a weak acid, is it product favored? Oh, and you cannot see the bottom of that, so let me make it so that you can. Okay, there we go. See if I can do one more. Yep. Okay, so there's the weak acid. I'll turn this a little bit so it looks a little straighter. Okay, so for a weak acid, weak acids are definitely reactant favored. So now that you know that weak acids are reactant favored, we can answer this. Equilibrium involving a weak acid and water is product favored. False. You can turn your mic on, Harry. That way I can ask you questions. You can say, yeah, okay. Are we good on this one, Harry?
Yeah.
Okay. You got nothing better to do on a Friday?
Not really. No, I got a rough draft I got to do later for English, but
Oh, I hate English.
yeah, it's not my favorite subject.
All right. So I'm going to give you a chance to read this one. Tell me when you're done reading it.
Yeah, no, I finished.
Okay, good. So we have two acids. One is boric acid. Now, when you look at a formula of a compound, there's usually an indication that this is an acid. When you look at the formula, you look for two things. One, it begins with hydrogen. If it begins with hydrogen, it's probably an acid. What does that tell you about H2O? Harry?
What, that it could possibly be one?
It definitely is an acid. It's a very weak acid, though. Okay. Another thing, often, except for H2O, the number of hydrogens, well, let me go back a bit. Another thing you want to look for in an acid, if it has this in it, or this, that means it's probably an acid. So for example, that's an acid. So those are the two things you look for in a formula to see if you have an acid. It has this Cu in there, or it begins with hydrogen. Are you with me?
Yep.
So is this an acid?
No.
No. How about this?
Could be a very weak acid.
That's actually a strong acid.
Oh.
How about this one? Let's see.
Yeah, that's an acid.
Definitely, because it's got the Cu in there. In fact, it's
Yep.
got two of them, right? All right. So those are acids. Now, for the acids, you also want to know how many reactive protons it has in there. How many of these hydrogens can react like an acid? Because the definition of an acid is that it produces H plus in water. So this guy up here, HCl, when you react it with water, this is what it actually does. But a simpler way to think about it is just that the HCl, when you put it in water, it makes H plus and Cl minus. So there's the H plus. So this is a simple definition that it produces H plus in water. It really produces this guy, which is called the hydronium ion. And when I post the lectures for this part of the chapter, you'll see that stuff in there. Okay, so it produces H plus in water. Now, some acids are weak acids. So we've got strong and weak acids. Let's take a look at those again. "100% ionization." HCl is an example of that. And then we have weak acids, which is incomplete ionization. Incomplete simply means less than 100%, usually on the order of less than 1% even. So there are lots of weak acids. This is a weak acid.
Does
So let me,
oh, I have a question. Does the little subscript number after the hydrogen or after the Cu, does it, if it's like a larger number, would it be more weak, or if it's,
it's never,
does that matter?
never a different number. It's always a 1. For this Cu, it's always 1.
Or like with the hydrogen one, does it matter what subscript comes after it for it to be strong or weak?
Good question. So let's take a look at a list of strong acids.
Because like phosphorus is H3PO4, and then
So
the HCl
these
is
are
just
strong
one.
acids, and you want to memorize those.
Oh.
Now, let me give you a list of weak acids.
But the Cu is always a 1.
Yep,
Okay.
these are weak acids. Now, look at this list of weak acids, and you'll notice a couple of things. Number one, that two of them have more than one hydrogen at the beginning, right? But they're weak. So does the number of hydrogens in the formula tell you whether it's strong or weak?
No.
No.
Okay.
So how do you know if it's strong or weak? Memorize it.
Right. Oh, okay.
Okay.
Alrighty.
Now also take a look at this guy. This is an interesting one. That's a strong acid, but this is a weak acid, and it's charged. So what does that tell you about acids? Do they have to be neutral molecules?
No. At least
They do not.
seems like it.
Does this begin with hydrogen?
Yeah.
That's what makes us think it's an acid. Let's take a look at what this guy does, okay? When you put it into water, it ionizes, and this is what you get. Now, why did I draw the arrow in one direction? And the answer is because it's a strong acid. Now, here, this is a weak acid. So what am I going to do for the arrow for a weak acid?
Is it going to go back and forth? Those
Exactly.
two? Oh.
So I'm going to put H plus here, and here you can see if I've used my H up to balance this, I'm going to have an SO4 here. And also the charges have to balance. Do you see how a -1 and a +1 is 0?
Mm-hmm.
And here
Yeah.
this is neutral, so it's 0. Well, this is -1. These two have to add up to -1, and so there you go. So the interesting thing is when you put this in solution, this is what you have. Those are the things you have in solution. You have none of this in solution. Why? Because it's a strong acid. It completely comes apart. Now, if you look down here, when you see the double arrow, that means you're going to see this and this and this in water, all three. Now, I guess if I wanted to do this kind of correctly, I should have drawn 2 hydrogens here, but I didn't. I just want to show you the different things that are in water. Are you with me here?
Right. Yeah, no, that makes sense.
Okay, so now let's extend this idea and look at a more complicated acid. Well, not a more complicated acid, but a different acid. So this guy here is called carbonic acid, and it's weak. So let's write the first reaction when it gives up one of its hydrogens. What kind of arrow should I draw here because it's weak?
Go in the opposite direction.
Right. Now, if I write this, what's going to be left over?
CO3.
HCO3, and what's the charge on it? Yes, H, because
Negative.
we've only used 1, right?
Right. And would it be a negative?
That's right.
Okay.
So this is a weak acid. This is also a weak acid. So what do we write here?
2 arrows going different directions.
And
Then an H
plus,
plus, and then just CO3.
do the charges add up? Is -1 equal to +1 and 0?
Yeah. Or say that again.
What does the charge on this have to be so that the charges are equal?
Oh, would it have to be negative as well?
Negative what?
-2.
-2.
Okay.
-1 on this side, +1 and
Oh.
-2 adds up to -1. Now it adds up.
So, okay. Oh, okay, that makes sense.
So you know how we balance by elements?
Yeah.
We also balance by charge.
Oh, you can do that.
Okay. So if we draw a little glass over here, what do we actually see in the water? Do we see any of this?
Yeah.
Do we see any of this?
Yeah.
Do we see any of this?
Yeah. You should see all three, right?
Do we see any of this?
Yeah.
Yeah, well, and we already have it written down.
Yeah.
Do we see any of this?
Yeah.
And we already have it written down. Do we see any of this?
We should.
That's right. So when you put this guy into water, you see 4 different things here.
Oh.
Now, if we talk about 2 of these, and you make 1 of these and 1 of these, actually, I'm going to say 3, and you make 2 of these and 2 of these, and then you take 1 of these, and you make 1 of these and 1 of these, let's figure out what we have left. So if you start off with 3 of these guys, after this is all done, how many do you have left? I'm going to do this a little differently. So do you see the 3 that I'm starting with?
Yeah.
1 of them stays the same. 1 of them does that, and another does the same thing. Okay, so here we're starting with 3 of these, and after the first iteration, we have this, these 2, and these 2. Are you with me?
Mm-hmm. Yeah.
Now, imagine after the next iteration, still nothing happens to this. These guys stay the same. And this guy comes apart. Are you with me here?
Yeah.
So here at the end, what do we have? We end up having 1 of these, 3 of these, 1 of these, and 1 of these. Are you with me?
Wait, 3 H plus?
Yeah, here's 1, here's 2, here's 3.
Oh, I didn't, yeah, okay, I see that.
So this is what's in the water bottle if we put 3 of these in here, just pretending that this is what they do. Fair enough?
Yeah.
Well, what would happen to the number of hydrogens if this was if this didn't happen very much?
Would it decrease?
How do I say this differently? So you see, this has to go through 2 losses, right?
Right.
What if this was a really, really weak acid and it didn't like to lose its hydrogens at all? What would that do to the number of hydrogens in the container?
Would it decrease it down to just 1?
It'd decrease it. That's right.
Okay.
So weak acids have fewer hydrogens in the container. Okay, so now we're at a place where we can actually answer this one here. 2 aqueous solutions prepared, 0.1 mole in 200 milliliters and 0.1 mole in 200 milliliters. So what they're trying to tell you is you have the same amount of each. They're both weak conductors of electricity. It turns out that if you take a solution and you put a light bulb in there and have this connected up to electricity, so here's your outlet. If it's a strong acid, the light bulb is really bright. And the reason is because ions help to conduct electricity. If you have a weak acid, the light bulb is dim because you have fewer ions in solution, okay? So when they say both are weak conductors of electricity, it means that they're both weak acids. But it says the H3PO4 solution was noticeably stronger conducting. Write equations to describe the equilibrium in each solution and explain the observed difference in conductivity. So let's start off with boric acid. And here we're going to do this the long way. It reacts with water and it makes H3O plus. So we're writing this instead of H plus. And H2PO4. Are you with me here?
Oh, okay, yeah.
So here we're putting water into the equation instead of not having it in there. Now, what happens with this guy? It reacts with water and you get H3O plus and you get HPO4. You'll notice this is a -1 and this is a 0. This is a +1, so this must be a -2. This is an acid. You put it in water, and it forms H3O plus PO4 3 minus. No hydrogen because it's gone. This hydrogen has been donated to that H2O. Okay, so these are the 3 reactions. So now, what are the 3 reactions for H3BO3? What's one of the products?
Yeah, sorry. Sorry, say that again?
These are the 3 reactions for phosphoric acid.
Right?
Let's look at the 3 reactions for boric acid. So it's going to react with H2O. What's one of the products for sure?
Well, would it be H3O plus and H2?
Keep going.
H2, what is it? BO?
BO.
3 minus?
Yes. What's the next reaction?
Is that, well, if it's like the other one, H2BO4 minus, or 3
BO3.
minus, sorry. And then plus H2O. And then you get H3O plus.
Right. Plus.
And then HBO3 2 minus.
And here, what are we going to get?
HBO3 2 minus and H2O. Is it just H3O plus and BO3 3 minus?
Yes.
Okay.
Okay, good job. Now, can you see that with every next reaction, you're creating more ions?
Yeah.
Here we only have 1 ion, and here we have 2. Here we have only 1 ion, and here we have 2. Every successive reaction produces more ions. Are you with me there?
Yeah.
Well, it turns out that more ions means more conduction. The more ions you have, the brighter the light. All right?
All right.
Now, if we look at the question here, it says, The solution with H3PO4 was noticeably stronger conducting. So this guy was stronger conducting. And this one was weaker conducting. How do we explain that?
What would it mean? The phosphoric acid would have more ions?
Yes, that's a very good start. More ions, less ions. So for this guy to have more ions, what does it tell you about this dissociation compared to this one? Which one ionizes better, left or right?
Left?
Yes, ionizes better. We're not saying that it ionizes completely. We're saying that it ionizes better, right?
Right.
Now, here's something else we can say. We know that if it doesn't ionize completely, it's a weak acid.
Right.
Well, what if it doesn't ionize as good as, what if they're both weak acids, but they don't ionize the same? They're both weak acids. Which one is weaker?
Those would be good. Or would the boron one be weaker? Since
That's right.
ionizes worse?
You got it, boric acid. Now, what I'm writing here, am I saying that phosphoric acid is a strong acid?
No.
No, I'm saying it's stronger than boric acid. So here, maybe one of the things that we could add to this is stronger conducting, this is weaker conducting, but this is weak, so it's a weak acid. And this is weak, so it's a weak acid. So if we look at what the text says, it says they're both weak because they conduct weakly. This is stronger conducting, which means it has more ions, which means it's the stronger of the two weak acids. And that's what we're supposed to get out of this.
Right.
Okay?
Right.
So let's take a quick little review of that one. Notice I did this. You're going to have to bear with me because this takes a little while.
It's okay.
So what I'm writing is what really happens in water. What I'm about to write is what a lot of people just go to as a default because it means the same thing, but it's just easier to think about. These mean the same thing. What's the big difference? And the answer is, here I show how the acid is reacting with water to make the hydronium ion. Here I don't show how the acid is reacting with water, and instead of the hydronium ion, we say H+. But these mean the exact same thing.
Right.
Now, if I write down the boric acid equivalent, it would look like this to begin with. What would the other two reactions look like?
Would be similar to the first.
Go ahead and say it to me.
So H would be H2BO3 minus, and then H plus HBO3 2 minus.
Excellent. And the last one?
HBO3 2 minus, and then the arrows, and then H plus BO3 3 minus.
Excellent. Okay, so remember, I wrote this out using water here, but if we take a look at these two, and we know this is a weak acid, and we know that this is a weak acid, and we know that this conducts better, and this conducts worse, what could we say about the number of ions here if it conducts better?
They have more.
So we can see that with each successive reaction where you have one ion, you get two. 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 Here, no ions and you get two. So which one of these is coming apart better, the top or the bottom?
Would it be the top?
Yeah, well, do we get more ions here?
Yeah.
So how do we get more ions? We have to have more reactions. So more reactions
Right.
means stronger acid. Not a strong acid, because we already said it's weak. It's a stronger acid than what?
Than what the boric acid is.
Right. So what I'm trying to show you here is that you don't need to write it out completely like this to come to the same conclusion. That's all.
Oh, it's handy.
All right. Now let's try a couple more problems here. Name and give the formulas of two acids that are strong electrolytes. So strong electrolytes means they come apart completely. So in your notes there, do you have the list of some of the strong acids I gave you?
Yeah.
So what are two of them?
HCl and HNO3.
Great. How about a weak one?
H2CO3.
There you go. Now, how about name and give formulas of two bases that are strong electrolytes and one that's a weak electrolyte? We haven't covered that yet. But bases usually are a metal hydroxide or ammonia. A metal hydroxide could be like that. Do you see the hydroxide here?
Yeah.
And the metal?
Yep.
Metal hydroxide. See this here? Is this a base?
Yes.
Where's the metal?
No, wait. No. Carbon.
Not a
No,
base.
it's not. Sorry.
So I tried to fool you and I did.
Yeah, you did. You did get me.
Because it's supposed to be a metal hydroxide.
Right.
This is not a non-metal hydroxide even. There's no hydroxide in here.
Oh.
Just because it says OH doesn't mean hydroxide.
Oh.
How do I know there's no ions in here? And the answer is, do you see any ion? Well, what are the elements here? Are they metals or non-metals?
Non-metals.
All non-metals. That means molecular. That means no ions.
Oh, okay.
Okay. Now, ammonia has this formula. So those are bases. Okay?
Mm-hmm.
Now, here are some strong bases. What do all of these have in common?
They all have hydroxide. But
You can see
no metals.
hydroxide in it. Good. Here's a weak base. What does the weak base have different than the strong bases?
There's no hydroxide? Or you
You
can't
don't see
it,
the
maybe?
hydroxide. Turns out that this does make hydroxide with water. And there's your hydroxide. Now, when I have these two arrows here, what does this mean? Does this react completely with water?
No. Wait. No. Or it's a weak.
It's
No.
weak. So that means that maybe some of them react with water and some of them don't,
Right.
right?
Right. So you can see.
So this is why this is a weak base. It only makes a few hydroxides. Okay, now you're supposed to name them. What's the name of this guy? Called hydrochloric acid.
Oh.
This guy is called nitric acid. And this guy is called carbonic acid.
Right.
Now, if you look at this carbonic acid, it looks kind of like this, doesn't it? Only with hydrogens.
Yeah.
This is called carbonate. This is called carbonic acid. Do you see the origin of the name?
Yeah.
And this one looks like, this is nitric acid or nitrate. So what would the acid be called?
Nitric acid.
Nitric acid. So if you have an acid what looks like it's made out of a polyatomic ion,
Mm-hmm.
you just take the polyatomic ion and turn it into ic acid. Like sulfate becomes sulfuric acid, carbonate, carbonic acid, nitrate, nitric acid, acetate, acetic acid.
Yeah, phosphate, phosphoric acid.
Phosphoric acid. You got it.
Yeah. Oh, okay. It's handy.
Okay. And the last thing we're going to do before we end it here is let's take a look at this. Which compound or compounds in each of the following groups are soluble in water? Now, there's a chart in the book that you really want to become familiar with that shows you what things are soluble in water. And here's the chart. Do you happen to have your book nearby? Or can you open it up in a window?
I can grab it 1 second.
Okay, cool. This is page 134 when you get it. That's page 134 again.
What page is it on?
134.
Right.
And it's at the top of the page. So we're supposed to answer which of the following is water soluble. So if we take a look here at the first set of choices, and we look at the chart here, here's how you use a chart like this. See how this says barium sulfate?
Uh-huh.
Well, if we look at what's written in white, you won't see barium anywhere. Okay?
Right.
If you look at what's written in white, we see sulfate right here. So soluble compounds are salts of sulfate. So what does salt of sulfate mean? Salt of sulfate means an ionic compound with sulfate in it. So salt is a very short word that we can say instead of ionic compound, okay? So, is this an ionic compound? And the answer is yes. How do we know? And the answer is it's a metal and a nonmetal. Metals and nonmetals are ionic compounds. Okay, so according to this, if we put this in water, will it dissolve? And this says that salts of sulfates are soluble. So what's with the yellow box? Well, these are exceptions. So this says that your sulfate will not dissolve if it's combined with barium.
Oh,
Is this a sulfate combined with barium?
yes.
So this is
Non-soluble.
insoluble.
Insoluble.
That's the term we use. Okay, let's look for something. We know there's nothing up here with barium. Let's see if there's something up here with nitrate. Oh, look right there. Soluble compounds, salts of nitrate. Is there any yellow exception area?
No.
So this
that
is
would be
soluble.
soluble.
How about carbonates? Do you see any rules for carbonates?
Yeah, it's over in the insoluble.
Insoluble. Well, there's exceptions.
Ah,
Are there any exceptions here
yeah.
that match what we have?
Oh, no.
Nope.
Oh,
So
yeah, no.
insoluble.
Okay.
And that's how we use this chart.
Right. No.
Let's go down to this next one. Is there any rule here for sodium?
Uh-huh.
What does it say about sodium compounds?
It's soluble. It says it's the first one. It says almost all salts of sodium, potassium, and
Soluble. You should just memorize this list.
right. Okay.
That way, if you see one of those in here, you're just going to say soluble. So
Oh,
how about the next one?
that one should be soluble.
What? Right. You don't even need to go beyond sodium, do you?
No.
Once you see the sodium, you're like, done, soluble. How about the third one?
So that one should also be soluble then.
Yep.
Oh, since there's no.
That's why it's nice to memorize these, is because it takes care of a lot of them. How about these?
Well, it does talk about Ag as a non-soluble exception, but it doesn't.
Well, remember, you want to focus what's on the white first.
Right.
So do you see anything about Ag in the white?
No.
Do you see anything about Br in the white?
Yes.
So they're soluble.
Oh.
What are the exceptions?
Halides of. Well, for the Br halides of Ag, Hg2, and Pb2, or lead.
So this is insoluble because we're talking about silver with bromine. So these are not soluble. You see that?
Right.
How about KBr?
That's soluble.
Right, because of the K. How about Al2Br6?
Well, there's no actually any mentions of Al in the white, but there's the mention of Br in the white.
And is aluminum an exception?
No.
Soluble.
So soluble.
That's how you do it.
Oh, that's not bad.
No, and if you can memorize which ones are soluble and which ones are not soluble, it helps. Let me give you the list of ones that you should probably remember for soluble. Group 1A cation. So we're talking lithium, sodium, potassium, all of them. You with me?
Yeah.
You should remember acetate ion, nitrate ion, and also I think the chlorate ion.
Okay.
So here you're going to say always. And this is going to be usually. These guys are usually soluble. Now, what are the exceptions that you kind of want to remember? The big exceptions are silver and lead. Mercury is an exception, but these are more commonly run into. Now, there's also sulfates, and their exceptions are basically group 2A cations like barium, strontium, calcium.
Then the
And
exception
in
to
addition,
the
lead is an exception.
Wait, what comes after group 2A cation?
Lead.
Oh. And those are the
Okay.
non-soluble ones?
What's that?
Those are the non-soluble?
Yeah, these are the exceptions. So barium sulfate, not soluble. Strontium sulfate, not soluble. Calcium sulfate, not soluble. Okay?
Right.
And then I have a list of things that are usually not soluble. Carbonates, phosphates, sulfides, oxides, and hydroxides. These are the most common ones you'll run into. Now, what are their exceptions? Their exceptions are the always soluble cations. So if you have lithium carbonate, it dissolves. If you have sodium carbonate, it dissolves. If you have potassium carbonate, it dissolves. If you have lithium sulfide, it dissolves. Are you kind of with me there?
Yeah.
So it's actually not a big list when you consider what we have here.
No.
Now, another way to do it is this way, Harry, is if you can remember these two, these are the ones that are soluble and these are the ones that are usually soluble. If it's not on that list, it's not soluble.
Oh.
So look at this guy. Is this on the first list? Is there anything about copper?
No.
Anything about chromate?
Nope.
So here we're going to say not soluble.
Oh, okay. That makes it easy too.
Yeah, if you remember these two, then anything else is not soluble. And it streamlines your life. You know what I mean?
Yeah. Yes.
So you want to know this, and then you want to practice this stuff on those precipitation reactions.
Okay.
So have you read the precipitation lab yet?
I did look through it earlier today, but
Okay.
I haven't sat down with it yet.
There's also a, in one of the lectures, I show you an example of mixing things together and doing a precipitation.
Okay.
So I think there may be video to go along with that you want to watch too.
All right.
Today I'll be posting the next lab, which is an acid-base reaction and a redox reaction. The redox reaction takes about 3 hours.
Oh, geez. Okay.
Yeah. And it takes about 10 minutes to set up the reaction, and then you have to wait 3 hours.
Okay.
So it's 10 minutes of work and 2 hours and 50 minutes of waiting, which hopefully you are doing something else.
Yeah, is that what, one of the next lab you said?
That's the next lab after precipitation.
Okay.
You're going to need vinegar, baking soda, and
Is it red cabbage?
red cabbage.
Okay.
Okay. All right, Harry. Thanks for attending.
Hey,
We'll
no
catch you
problem.
next week.
All right. You have a good one.
You too.